Unit 13. The behavior of gases. So that's what we're taking a look at the next couple of weeks here. And this year being what it is unit 13 of 14. So we are getting close. So looking at gases, like the air around us, air that we breathe, the atmosphere, all this gases. What happens to gases when they're in different scenarios? That's what this unit's all about. Starting off today, taking a look at two laws. Charles's law and Lussac's law. So two different laws. We'll take a look at them both together as we go through today. So 13.1, Charles' law and Guy Lussac. I believe they were both Frenchmen. Not sure what the French's affinity for gases were during the 1700s, but I believe they were both Frenchmen. They both kind of came up with these different laws that govern how gases behave. Hey, real quick, a lot of you guys at home, you need to get yourself in the camera. I need to see you in the camera. There's like 3 or 4 of you guys that the camera it isn't on you. So get yourself in the camera so I know you're there. So before we really get into these laws, these gas laws, couple of house cleaning things we have to do. First of all, something we call absolute zero. Kind of a weird concept. With numbers, we know that numbers go on or can go on forever. You can have infinity. Just keep counting. And that's the same both in the positive direction, so above zero, and in the negative direction. You just keep counting forever and ever and ever and ever. It's kind of how numbers work. That's not how temperature works, though. Temperature has an absolute zero. It has a number that is the lowest possible temperature, and that number happens to be negative 273 degrees Celsius. So that's what we call absolute zero. But here's the problem. We can't work with negatives. We can't do it. Guys, we're working with volumes and temperatures and pressures. What is a negative volume? What is the opposite of a volume? Something that takes up space and has mass? How can you not be like? What is a negative volume? It doesn't exist. It's a contradiction. So we can't have negative volumes. It's just not a thing, which means we can't have negative temperatures either. So what we did is we invented this new scale. It's called the Kelvin scale. Kelvin is symbolized with a capital K. There's no degree symbol, though. I don't know why. But, Fahrenheit and Celsius have degrees. Kelvin doesn't have the degrees. It's just a capital K for Kelvin. And it's really simple. It's the same as Celsius, except plus 273. And that way, your absolute coldest value is 0. And you never have to go negative. The lowest you can possibly go is 0 degrees Kelvin. Excuse me, I said that wrong. I can't have degrees in Kelvin. It's 0 Kelvin. Hey, for this unit, always, always convert to Kelvin. So get in the habit of doing that. You will have incorrect calculations, whether they're negative or not. You're going to have incorrect calculations if you do not convert to Kelvin. So get in the habit. Whenever you see a degree Celsius, just add 273. We have to working in Kelvin for this unit. Questions so far? Well, let's get on with the first law then. Good old Charles. All right, so we are taking a look at Charles's law first. Charles looked at the temperature and the volume of gases. And Charles found that the temperature and the pressure, sorry, the temperature and the volume of a gas are directly proportional. For those of you guys forgotten from, whenever it was you took algebra, directly proportional means if one goes up, the other goes up. It's a direct relationship. You guys know I like my drawings. All right, so here we have a, oops. You guys gotta let me know about that. All right, so here we have a volume of gas. Little black particles are gas particles, we're saying. I've got 10 of them. Yes, the number's kind of important. You got to make sure that stays constant. But this right here is our initial volume, V1. How much area are those gas particles taking up? And then over here, I will draw a thermometer and we'll measure how much heat is being added. And that is our T1. So if I have these gas particles and I'm applying this heat, whatever this heat happens to be, and then we turn the heat up, we got a lot of heat. Look at that big old flame, me and my artistry here. So my heat is way, way up now. What do you expect to happen to our volume? heat goes up and our temperature goes up, guess what? Hey, we just talked about it. If one of them goes up, the other one goes up. I have a larger volume now, a larger area, because I have more temperature. Still the same number of dots. I can't change my number of dots. I would be changing my amounts, and that wouldn't be right. So if I put 10 dots over here, I got to make sure I get those same 10 dots over here. There we go. They've just got more room to spread out in. More temperature means more volume. One goes up, the other goes up. Vice versa, though, too. If your temperature goes down, your volume is going to go down. Mathematically, that relationship can be shown like this. V1 over T1 is equal to V2 over T2. Questions? Everybody's good so far? All right, well, let's take a look at what this looks like. Here's what here's what a lot of this chapter is going to look like. For some of you guys, I apologize ahead of time. So there's a lot of what this unit is going to look like. Word problems. Sorry for those of you guys who are not big fans of them. That's a lot of what this chapter looks like. So this example states, if a sample of gas occupies 6.80 liters at 325 degrees Celsius, what will its volume be at 25 degrees Celsius if the pressure does not also change? All right. Well, hey, we can all use some help and some work on word problems and algebra and all that. So something I strongly suggest, especially if you're not a fan of word problems at all, write down your variables. Make a list of them. List them out. Here's what I have. Here's what I'm trying to solve for. Here's how I'm going to solve for them. So let's go back. If a sample of gas occupies 6.80 liters, well, guess what? That is a V1. That's my initial volume. So I'm going to write that out. List that out. Okay, I have that to work with. And my initial temperature, so that 6.8 liters, is at 325 degrees Celsius. So my initial temperature, 325 degrees Celsius. Then it says, what will its volume be? Okay, so they're asking for the second volume. That's unknown, V2 equals question mark. That's what we're trying to solve for in this problem. Our second temperature, our temperature changed to 25 degrees Celsius. There we go. One last thing you have to be in the habit of doing. we can't work with degrees Celsius. Not this chapter. Not this chapter. So we got to convert that to Kelvin. It's a really easy conversion. 325 plus 273. There we go. 598. Same thing with this one. We cannot work with degrees Celsius. All right, so now we're ready to start setting up our problem. Guys, another thing you have to get in the hang of, isolate your variable first. I know you don't like doing that. I know it takes time. I know it's not fun, but you are much, much less likely to make a mistake. I'm not saying you're guaranteed to make a mistake, but you're much, much less likely to make a mistake if you set yourself up to succeed. So let's see, what was that formula we just looked at here? V1 over T1 is equal to V2 over T2. So that's what we're going to use. And again, this is Charles's law. Charles's law. And so what I mean by setting up your work is let's isolate the variable. Let's figure out what we need to do to get what we want. We want V2. That's what we're looking for. Let's get V2 on a side by itself. Let's isolate it before we do anything else. Before I put in any numbers, before I crunch any math, let's get V2 on a side by itself. The way that we do that, we have to get T2 out of here. So we have to do the opposite operation. If we have V2 divided by T2, the opposite operation divided by multiplied. So T2 times V1 over T1 will give us V2. Hey, look at that. Now we've set up our problem. We've gotten our second volume on a side all by itself. Now we're ready to plug in our numbers and solve. Another big thing, guys, if you don't show units, even in your work, on your homework, you aren't going to get much points. I will not give you much credit if you do not have units. You have to have units. You must have units, even in your work. So let's see, my T2, that was 298 Kelvin. Put that K there. Do not just write a number. I'm going to subtract points upon points upon points. If you do not put that little unit right there, we're in no hurry. You got like 5 problems as your homework tonight. Not going to take you that long. Slow it down. Show me your units. The times are V1, and that was 6.80 liters. Unit, show it to me. And finally, our T1, that was 598 Kelvin. All right, so all of that is going to equal our V2. So now we're ready to plug it all in. Wow, I'm writing gigantic today. Three significant figures, 3 significant figures, 3 significant figures. So 3.38, those are our 3 significant figures. The next number is an 8, so that means we're going to round up, and we'll call this 3.39. The Kelvin cancel out, right? Kelvin divided by Kelvin is nothing. It's 1, I guess. And we're left with liters, which makes sense because we're looking for a volume. Oh, by the way, V is not a unit of volume. V stands for the word volume. So you can't just say, I put a V right there. And no, put a unit of volume. Probably, since it's a science class, we're working with liters or milliliters. I always like to double check then. Let's see here. Our temperature went down. It's a direct relationship. If our temperature goes down, I expect our volume to have gone down. 6.8 to 3.39 is definitely going down. So yeah, everything's checking out. It all makes pretty good sense. Works for me. Questions? Good so far? All right, just one more law to learn today then. This is Lusac's law. Lussac worked with pressure and temperature. And he found that pressure and temperature, like temperature and volume, pressure and temperature are directly proportional. So again, that means the one goes up, the other one goes up. That's what a direct relationship is. All right, so we've got two containers. I'm not going to change the volume. This one's 1 liter. This one's 1 liter. We're not worrying about volume for Gay-Lussac. 1 liter, 1 liter. I'm going to put 6 little molecules of gas in here. And one of the ways that we measure pressure, can kind of show pressure, is with arrows. These things are moving around. And I've got small arrows. They're not doing a whole lot of moving here right now. Just kind of moving around. But one of the ways that we look at pressure is how much are they colliding with the walls of their container? And when they do collide, with how much energy do they collide? You know, they hit the wall really, really hard, really fast. They're just kind of scraping by it. That's kind of how we measure pressure. So I'm going to say we are working at 150 Kelvin. And our pressure is 1 atmosphere. ATM stands for atmosphere. It's one of several ways that we have to measure pressure. We'll talk about a couple of the other ways, not all of them, but all of them, not this year at least. But the atmospheres is one of the ways we have to measure pressure. The idea being, sitting here right now, or especially when you go outside, we don't feel it, largely because we've never known anything different. But there's 5 miles of air sitting on top of us. That's a lot of pressure. It's actually a significant amount of weight. Again, we don't feel it. We don't know any better. We've never known any different. But there are 5 miles of air, as light as air may be, 5 miles of it up. It's going to weigh down on us a little bit. How much? Well, we call it 1 atmosphere. 1 atmosphere. As that increases or as that decreases, we know that we're working either, above what you have outside or below what you have outside or whatever it happens to be. But 1 atmosphere, that's one of the ways we measure pressure. And again, the atmosphere is like what you normally feel on a normal day. All right, so 150K, that's pretty cold. Really cold, actually. Put a little flame on there. Let's bring that temperature up to 300 Kelvin. Well, guess what? Can't change my number of dots. I have 6 over here. I got to have 6 over here. At 300 degrees, much, much warmer. My volume didn't change. These guys are going to be moving around a whole heck of a lot more. And when they're moving around a whole heck of a lot more, they collide with their walls of their container a lot more and with some more force. And that's how we have more pressure, more interactions of these gas particles with their surroundings. And hey, if our temperature doubled, 150 to 300, that's a double, our amount of pressure will double as well. Mathematically, P1 over T1 is equal to P2 over T2. And that's Lusac's law. Again, some common units of pressure, because you will see these. There are others also. I just don't know that we're going to see them this year, but common units of pressure. So the one we just talked about is known as an atmosphere. We measure it in what we call ATM. That's the abbreviation for atmospheres. Another common one you're going to see is called the kilopascal. The symbol for that is kPa. Hopefully we're pretty familiar at this point in the year with kilo. So kilo means 1,000. So it's really like the base unit is a pascal, but it's a really, really small unit of pressure, the pascal. So we just kind of use the kilopascal. So we're talking about larger denominations of it. So kilopascal. And then finally, the one we are all probably most familiar with. The one we use here in America, because we work with pounds and inches, is PSI, which stands for pounds per square inch. So if you guys ever paid attention to like how much or what your tire pressure is, like in your cars, how much air is in your tires, we measure that in PSI. And you're usually wanting, depending on the vehicle you have and the type of tire that you have, you usually want your PSI like the mid 30s. And your car usually gives you a little warning, a little ding if you get into the 20s. Tire pressure is too low. So we measure tire pressure in PSI. Questions? Cool. So look at an example. Sorry, I'm writing really large today, so I keep flipping to new pages and all that. You guys may not be. That's fine. All right. So quick example of Lusac's law. All right, the pressure in a sealed plastic container is 108 kilopascals. Hey, so there's our unit of pressure, kilopascals, kPa. That's at 41 degrees Celsius. What is the pressure when the temperature drops to 22 degrees Celsius, assuming that the volume doesn't change? All right, well, again, I like to list out my variables. Let me see what I have to work with. What am I trying to solve for? What kind of formula am I going to be using? My P1 is 108 kPa. My P2, what's my second pressure? What? Oh, they don't give that to me. What is the pressure? So my second pressure, I don't know. I need to solve for it. My initial temperature, well, I said my 108 pressure was at 41 degrees Celsius. So that's my initial temperature. And then my second temperature, I say the temperature drops, so it changes to 22 degrees Celsius. There you go. Hey, again, first things first, we can't work with degrees Celsius. So we got to convert to Kelvin. So 41 degrees Celsius plus 273 gives me 314 Kelvin. 22 degrees Celsius plus 273 gives me 298. Oops, 295, excuse me. Losing it already. Such a beautiful day out there. Where is my mind? All right, there we go. 295 Kelvin. All right, once again, we need to set our equation up. We need to set ourselves up to be able to solve this problem. We start throwing numbers at it and give ourselves a headache. Will you sometimes get the right answer? Yeah, sure, you will. Some of you more than others. But if you take your time and set this problem up correctly, you put yourself in a much better place. I know it takes a little bit more time, but that's okay. Like I said, you only got a couple homework problems tonight. So we are working with Gay-Lussac's law. P1 over T1 is equal to P2 over T2. We're looking for our second pressure. It's this guy. So we need to get him on a side by itself. How do we do that? Well, the opposite of divided by T2 is times T2. So we'll times both sides by T2. We'll end up with T2 times P1 divided by T1 is equal to P2. There we go. Now we're ready to plug in the variables that we have. So our second temperature, 295 Kelvin. Don't get lazy on me now, Dotson. Units, put that Kelvin there. We multiply that by our initial pressure, which is 108 kilopascals, and divide by our initial temperature, which is 314 Kelvin. Cool, now ready to solve? Can make sure you have your units in there. Those are going to be worth as much, if not more, than the actual numbers this unit. So 295 times 108 divided by 314 is 101.4649. Three significant digits, three significant digits, three significant digits. The 1, the 0, and the 1. The 4 after the 1 is not enough to round up. So just keep it at 101. See, Kelvin cancels out. We're left with kilopascals. That's absolutely fine. In fact, that's good. We're looking for a pressure. That is a pressure. And I always like to kind of double check, though, too. Our temperature went down from 314 to 295. We'd expect our pressure to go down as well. It went from 108 to 101. So, yeah, Yeah, it all checks out. I think that makes good sense. Questions? All right, one more example for you guys on such a loose. Always like to make sure we do one with temperature. Sometimes the algebra can be a little bit trickier when you're trying to solve for a temperature. So make sure you guys see one like that. One more example. All right, so this time, a little bit different. Some people sometimes struggle with the algebra and problems like this. This time we have the pressure in a car tire is 198 kilopascals at 27 degrees Celsius. After a long drive, the pressure is 225 kilopascals. What is the temperature of the air in the tire if you assume that the volume stays constant? Well, all right, again, write down what you have. Get yourself started. P1, my initial pressure, 198 kilopascals. P2, okay, after a long drive, my pressure has changed. It's now 225 kPa. My initial temperature was 27 degrees Celsius. Remember, though, we can't use Celsius. We have to convert it to Kelvin. And yes, that decimal point is really important. Remember significant digits. For an addition problem, it doesn't matter how many significant digits you have. What matters is where the last one is. So 27 has its last significant digit in the ones place. 273 has its last significant digit in the ones place. So we have to have our last significant digit in the ones place. So that 0 has to be significant. The way that we do that, by putting a decimal there. Now they're all significant, 3 significant digits. All right. And our second temperature, well, hey, that's what they're asking for. What is the temperature in the air at the end? So that's what we're trying to solve for. All right, just like last time, have to remember our formula. We'll start with that. Again, this is Lussac's formula, law. All right, so a little bit different than last time now. We're trying to find T2. Now, T2 is on the bottom. A lot of times people do this upside down or backwards or whatever. They end up with the inverse. That's not what we want to do. So in order to get T2 on a side by itself, we also first have to get it on top. That's going to take an extra couple steps. I don't just want it over here on the side by itself, but I also want it on top. So I do that first. I get T2 on a side by itself first. The way that I do that, if it's on the bottom, I multiply both sides by T2. I know it kind of looks like I'm solving for P2 here, but I'm not. I'm still going to try to find T2. I just need to get T2 on the top. Now that I've got T2 on the top, now I can work to get it on a side by itself. First thing I want to do is get T1 off the bottom. So I multiply both sides by T1. That gets it off the bottom. Second step, then, we got to do the opposite of multiplication. So divide both sides by P1. And there we go. Now we've got our T2 on top and on a side by itself. We are now ready to put in our variables, put in what numbers we have to work with. Let's see, our second pressure was 225 kPa. Our initial temperature, 300 Kelvin, and yes, the decimal point is important. And our P1, 198 kPa. Cool, so now we're ready to solve. Three significant digits, that decimal point's important, and 3 significant digits. So 340, there's my 3 significant digits. The 9 afterwards, not significant, but it is enough to make me round up. So 341, let's see here, my kPa canceled out. We're just left with Kelvin. That's good because we're looking for a temperature. The question didn't say in Celsius. Sometimes it does. Sometimes it does say in Celsius, and then you have to subtract 273 to get back to Celsius, but it doesn't say it, so we can just leave it at Kelvin. There we go. Our new temperature will be 341 Kelvin. Again, always good to double check. Let's see here. Where pressure went up 198 to 225, so we'd expect our temperature to go up. It did. I think we're in pretty good shape.